Oh, and we're good to go. So I'm very happy to introduce at EMF Camp, the Tim project, making a relay computer out of scrap, and Rory Mangles. So big welcome.
Hello. So, first things first, my campsite is right next to the bar, so unfortunately, I might be a little bit more rusty than I would usually be. This is the Tim project. This is the story of kind of how I learned about computing. So, back in 2010, I was about to start my GCSEs, just finishing my GCSEs, start my A levels, and I hadn't really decided what course I wanted to do, but electronics looked interesting. Never done it at GCSE level or anything before, so had a look at that. First module was on logic gates and various things. I was like, oh, that's interesting. Don't know how those work, but because I haven't done any of the electronics before, I'll do some research before I actually go on the course. And so I started looking on YouTube for videos on how logic gates work and just general information. There's a really good YouTube video on how to make a half adder out of transistors. And I said, ooh, what's a half adder? That sounds exciting. Or it does to me. So I, rummaged around in the shed and wanted to see if I could make anything out of, make a half adder out of everything. And the only electronics, or really electrics, that I'd done previously, I played around with a couple of relays a couple of years ago previously, just to make some little circuit or something. It probably didn't work anyway. But I had relays, and they're really difficult to blow up, so I was like, okay, we'll play with some relays, make a couple of circuits out of that. So I set about making this circuit that's up on the screen. It's really not the simplest way of making a half adder, it turned out, but I didn't know that at the time. It was only this way of doing it because it was all done in transistors. Relays are much easier to use, it turns out. I soldered together some relays, and obviously, I'm assuming everyone knows what relays are, but if you don't, they're electromagnetic switches that are powered by a little coil in there that just splits the switch. And just at the bottom there, showing an AND gate. So you turn the two A and B lines on, and it sends a signal to the output. It's closed-based switches. It's fairly straightforward to concept, which is why I was using them, because they're really easy to say. I got hold of a couple of relays, soldered them together to make a couple of logic gates, and then soldered those together to make what became TIM1. So this is the very first bit of computer logic I ever made. It took me an afternoon, and I was very pleased myself. I added a 1 and a 0, or a 0 and a 1, or a 1 and a 1, and it gave outputs on those old motorbike lights that I had lying around. And it was very poorly wired, and it was, pretty basic and much more complicated than it needed to be. But it was really exciting to me because, I didn't know how any of this worked before, and then I'd, thrown together some parts, and I had something that was doing maths. Really basic maths, but it was really, for a 16-year-old me, it was very exciting. And I had added one bit of memory in there that just held a light on when it was turned on. Very simple, but I had a computer with memory. It was all good fun. So I then made TIM2, which was basically the same thing, but with another bit of memory. TIM3, I took the whole thing apart and rebuilt it, found a proper power supply, found a little box, and made a little 3-bit full adder, really going up in the world. At this point, I'd realized that circuit design for an adder was a terrible, terrible idea, and redesigned it. And that whole of the previous circuit was condensed down to about 4 relays rather than 10 or so that was there. And that allowed me to put together a whole load of extra bits and make full adders instead, which meant I could now add up to 16. Almost use it in my exams, but not quite. So this was the point where it started getting vaguely serious. So I was like, okay, this is cool, but what if we go bigger? So this was Tim 5. This was the monstrosity that was Tim 5. Basically, I got Tim 4 was just a Tim 3 with a bit added on to make it do up to 4 bits rather than 3 bits. Tim 5 was Tim 4 plus a load more memory and calculation, sequencing circuits and stuff. So in the middle there, we've got 2 4-bit registers, which hold data as it's going through the computer. Those are all made out of car relays. And the reason why this project is titled Making a Computer from Scrap is because I didn't buy anything for this. This was all found crap around the farm that was around the place that was stolen stuff. So a lot of these are car relays, a lot of these are out of old cash machines that were made at the farm. And a lot of them are, like washing machine stuff and out of a microwave or whatever I could find. And this lovely item was wired up pretty much. I put down a relay and then soldered it up where it was. And it meant you ended up with what you see there, which is, amazingly it worked. And there's a video online of it working. It could count up and do multiplications. So you put in 2 numbers and it would add the number another number to it repetitively to basically multiply it. And it was 4 bits, so it could do up to 32 in total with the carry bit. And it worked, but I was like, right, kind of need to rebuild this because I can't move it because it's a pile of relays on a desk all loosely wired together. So I built Tim 6, which was basically the same idea, but everything had been rewired. And just to give you an idea of the problems I was starting to get of not designing any of this beforehand, putting relays down, soldering them up. On the right there, you can see the wiring on the underside, which is not, a wireman would scream in horror at that. It's all point-to-point rat nest wiring rather than any looming of data bus or anything. It's just, what's the shortest bit of wire I can use to avoid spending money on it? So it was, again, all found parts, which is why nothing quite matches. And you've got different car relays on the left and right doing the memory, and then all sorts of mishmash of stuff in the middle. But yeah, so this thing kind of worked, but there was a fault in it. Turned out after many, many months and while I was taking it apart again, turns out one of the capacitors in the top right had a dodgy solder joint, but I didn't know that at the time. But basically, the problem was I had no circuit diagram. And when you've written a bit of code and you didn't bother putting comments in, and then you come back and a couple of months later, it's like, I have no idea what any of this does. This was basically this whole project up to this point. So I was like, right, I want to redo this properly. So I want to do, at this point, I still had a calculator, so it was just add numbers, but there was no program. It just kind of did exactly what it was wired to do. So I was like, right, I'm pretty sure at this point I could make a full computer. This is about a year later at this point. So I spent up to Tim 6 was a couple of months of playing around with relays. I was like, right, I want to do a proper computer, but I am going to have to do some proper circuit diagrams. So most people at this point would download some circuit diagram designing tool. I opened up Microsoft Paint. Don't do that for your circuit diagrams, but I didn't know any better at the time. As I say, this whole thing's a learning project in many ways, more ways than one. So I was kind of trying to learn computing, electronics, wiring, soldering, all at the same time. So a lot of it kind of shows badly with that, but things were working up to this point. So, the other problem I had with building a whole computer is like, I only have what I could find. I didn't want to buy any relays because those cost money, and I, at that point, was still a school kid. I wasn't earning much money. So I was like, right, I'm not going to waste any money on relays. So I scrounged around as hard as I could, managed to scrounge about 200 relays. So I was like, what can I build out of that? So I started designing things, and these are some of my beautiful paint arts that I drew up. I still don't know why or how I managed to draw such nice diagrams in Paint, but as you can see there, basically the idea was on the left was the first design, which is basically TIM5 with the 4-bit registers and a much bigger, more complicated arithmetic logic unit, the ALU in the middle, and that could do different things. Had this huge multiplexer at the bottom to get all those different 4-bit numbers down to one 4-bit number and put that in another register. And then I was like, oh, 4-bit, I've got some spare relays, I could probably squeeze out to 5-bit, but that makes the ALU even bigger. And at this point, just a 5-bit ALU is going to cost me like 40 relays, and then the multiplex at the bottom is going to be another 40. And I was using most of my relays. Like, I don't really like this design. It's not a neat way of doing things. So I came up with a 1-bit ALU, which would actually only use 12 relays in the end. But I realized that if I switch through every single digit in the register individually, and just have a little bit of memory that saves the ALU state as it's going through, I can actually just do a series ALU, so it does one bit at a time, which has the benefit of A, less relays, but B, variable bit width, so I could then have it 4-bit, have it 8-bit, have it 32-bit if I wanted to, if I had that many relays. So at this point I was like, all right, well, that's just saved me a ton of relays. Let's go 8-bit. So I designed this thing to be a full 8-bit Turing-complete computer, and as you do out of 200 relays, the whole thing runs on punch tape. So the main problem with relays is trying to get memory. Memory is expensive in terms of every bit is at least 2 relays, and you have to have multiple registers of 8-bit wide, and you don't really want to do that. So to store the program, I made this punch tape stuff. So we had a lot of receipt printers around, and I hacked one up to be a tape reader, and then I hacked another one to print punch tape. So what it has is a load of LEDs and photodiodes that, as this tape's going through it, reads the tape off it, reads the program off it. And instead of most computers where you'd run the paper tape into the memory and then run it from memory, this one runs directly off the paper tape. You can see down the side here there's a clock pulse that clocks the relays as it's going through. So this meant I could have infinitely long programs in my Turing-complete computers. I could do whatever crazy things I wanted to do with it. But obviously I still had to build it at this point. So I designed this great thing, and I was like, all these plans, like, never am I ever going to get this built, but let's go, let's try. So I built these. So first I built the ALU just to check obviously the 1-bit ALU idea works. It was great. It worked, with a bit of tweaking, with a bit of debugging, it worked exactly as I planned. So I was like, that's cool. Let's add some registers to that. So that made the ALU unit. Then I was like, right, I've got to work out how to control this thing. So I had to basically hard code. I came up with an instruction set, which is as simple as possible to implement. So there's 8 bits on the punch tape. First 4 bits are the address for that instruction, and the second 4 bits are the instruction itself. And these were entirely designed to be as simple as possible to encode into a relay computer just using the wiring. So I was like, right, I've designed this instruction set. I've got to try and wire this in, hardwire this design of instruction set into the relays. So I managed to get that bit working. And at this point, it had to get the tape reader working, and that took me a very, very long time because it kept, for some reason, the photo transistors kept dying, and I was like, I was used to relays, which they don't die for anything. And I was like, stupid modern technology, being really difficult to use. Turns out the earth lead had fallen off my soldering iron, so it was frying it all with like 240 volts every time I was putting it through. Obviously very low current, so, and the way I picked this up is because I was like, right, I'm going to do full anti-static, and have the mats down, have the wristband on. When I was soldering something up and touching the other end of the wire, I was like, ow, ow, ow. It's like, that's not ideal. Why is that getting what feels like mains volt? Oh, so after I fixed that, the tape reader worked. So that was that problem fixed. At this point, again, it was just a pile of relays on the table, so I had to come up with some way of moving it around. So I was like, right, well, nice, I want to be able to see it all, and have it all fold up. So if I put get a nice big set of plastic seats, a couple of hinges, I can put the Logic unit at the bottom, that's the biggest, heaviest bit, that's nice and, ballast. Put the control circuitry on the side, that'll go there. Registers can go on the other side, it's quite neat. And then, tape reader goes in the back. Nice split out front, perfect. So that's kind of how this thing came about. The whole thing is, oh, crap, go back one. Not used to using this on Google Drive. There you go. So, yeah, good. So, essentially, this computer runs on Harvard architecture, which is the idea of it runs off the paper tape rather than on the computer memory itself. So it has a separate store for program and data. The computer has 5 registers, 1 working register and 4 down the side as the general use storage registers. And then I came up with a way of doing a really basic memory type using capacitors and diodes. So I've got 16-bit, 12 bytes of capacitor diode RAM. And the whole thing in the end used 160 relays, had a full 8 hertz clock rate, and a full 16 bytes of memory if you include the registers. So blistering speeds, and not quite running Crisis yet, but amazingly, after I've wired it all together and spent forever debugging this, and I mean forever, it's still my beautiful rat-nested wiring. I didn't learn anything on that was fun at this point. Still trying to use as little wiring as possible. There's probably several thousand solder joints in there, all badly done by 16-year-old me. None of it's insulated. All of it runs on 12 volts, fortunately, for everyone's sake. It consumed about 5 amps of power when it's up to full chat, and can do basic addition, entirely worth it. But the whole point of the project was, I just found an idea of, I realized I could build computers out of relays. I was like, okay, what's the logical extreme of doing this with what I've got? And so what we ended up with Tim 8. By the way, the name Tim, I just had to pick a name, and Tim was a good name. So I pretended it was an acronym for a while. I was like, no, I just picked a name at random, pretty much. But yeah, I ended up with. So Tim 8 is the kind of culmination of the 2 years that was that project. And I took it around various places doing talks. It turns out when you have a whole computer made out of relays in a really nice clear box that opens out on the table with all the different chunks, it's actually a really good way of teaching computer hardware. Because one of the problems is, these days, or at least in my opinion, is that everyone learns software these days, or at least everyone here probably learns software, how to write programs and how to do Python and all the rest of it. But how does the computer work? You give out kids Raspberry Pis and all the rest of it. And it's like, right, there's this magic black box. If you put code in, it does these magic things. So how does it work? Don't know. It has millions of transistors to do crazy things. Okay, do you have a picture of it? No one has a picture of it. Whereas this thing, you can open it up. It's like, there's the registers. They're about this big. You can see them. There's the ALU, the logic unit. It does number things. There's the control circuitry. There's the program on a punch tape that's reading through it. Here's all these flashing LEDs that you can see the program stepping through at 8 hertz rather than bang and it's done. So, I mean, although this was a learning tool for myself, it's actually been quite a good educational tool, having taken it around a few schools, and just showing this is how computers work. And it's been not the most reliable piece of kit, as you can imagine, but and in a minute I'm hoping to demonstrate it and see whether it survived the trip from the car to my tent and then the tent to here. But I've already covered that. Just going back on quickly on the program, I made a program called the Basic Language of Tim, or BLT, which is a nice sandwich. Again, my naming schemes are entirely arbitrary. You can see here on the right the instruction set that I wrote for it. So you've got 8 different logic processes. You've got addition and then a load of simpler ones. You've got all the addresses at the bottom left for all the different registers. You can load to, load from. Looping on a punch tape is interesting. instead of like a normal program where you can just jump, this is the kind of more traditional Turing machine style of when it sees a loop command, it has to rewind the tape until it sees a start loop command, and then it runs it forwards again. If statements are similar, so you have, if it sees an if statement, it just stops, it keeps running the tape, but it stops executing commands until it gets to an end if, and then it'll start executing commands again, unless that statement isn't true, in which case it'll just run as usual. So there's a lot of interesting working around on the punch tape there, but I think it's technically Turing complete. Turing complete is quite a difficult definition of all the different things the computer has to be able to do. But I think with conditional branching, aka the if statements, and looping, it can do it. It can kind of do nested loops. Obviously, being able to loop within a loop is difficult. I did kind of implement that, but yeah, it's a lot of things in this computer kind of work. Yeah, I mean, the basic, I mean, I did actually write a program in the end that could do full simultaneous equations that to solve simultaneous equations using matrix algebra, which was about 10 meters long. I never printed it. I wrote, for the sake of myself writing programs, I wrote a assembly language and a simulator so I could run it all on the computer first before printing it out, because debugging on paper tape is a nightmare. So I wrote some ridiculous programs for this thing. Probably the most complicated program it's ever managed to actually run is the Fibonacci sequence, which is a lot simpler. Recently I added, basically, Tim had been sat under my bed for the last 5 years, haven't really done anything with it. But recently I hauled it out, blew the dust off it, and fixed it up. Because basically there's this fairly terminal problem of somewhere buried deep within the wiring, one of the relays had died, and it was one of the important logic unit relays. And I found which one it was many years ago, but just never managed to work out how to get it out. So, and various over the years, I'd say, right, I'm going to do this now. No, it's way too much effort. So this is another, right, I'm going to do it. Plugged it in, turned on, the relay started working again. So I was like, right, run with it, it's fine. So on the, so I got it all working again, mostly. It's to the point it could run programs at least. And I was like, right, the one thing that always really annoyed me about this is you'd run a program and you'd have nothing to show for it except for the lights at the front. You always really wanted a printer. So I tried designing my own printer and all the rest of that. And it didn't really work, as you can imagine. So it's like, but these days it's like, right, I know a bit more about electronics and stuff, having now done my degree in electronics and going away and spending many more years doing electronics after this. So how, I kind of know a bit better about protocols, and turns out printer parallel ports are about the simplest possible protocol you can use. So I stuck a parallel port on it and wired that in, and it can now print with the tape reader. So I plugged it into the same tape reader it does with this. The text is very small because the default text in that is pretty tiny font, but technically I can plug this into any printer and it'll print out. So you can use it like a teletype terminal. It's great. In theory, if you know your ASCII codes and are good with switches. Keyboard's next on the list. But basically, this then allowed me to write the program that everyone always does when they first do it. It's now can do Hello World on a Relay computer, which was very satisfying. So yeah, we'll give it a try. I can't promise anything, but unfortunately, the tape reader is got a little bit worn out. So it's a bit sluggish on actually reading the program, because the program, the clock speed is set by the motor and the grip on the roller in the tape reader. So it's not the most reliable setup, but we'll see if it works. So the power on switch in the front. We've got the 5 registers up the front here, which that's the working register at the bottom and the 4 main registers. A nice big rotary switch on the side for selecting which you write to. You've got all the switches at the bottom that give you the option of manually writing data to the registers. And yeah, currently we've got the Hello World program ready to go, so I'll boot it up and see if it will go. LEDs in the front should start lighting up if it works. I'll manually feed it, it's fine. So that was hopefully printed out Hello World. Well, it printed out Hello World twice, but that's close enough. it kind of survived the night in the tent, but I'll just open it up just so you guys can have a better look inside. If anyone wants to ask any questions while I'm doing that, then go ahead. I've ran out of slides, so that's me done for the day.
Okay, cool. So I've got a question actually. So how many hours in all do you reckon it take as you put into this?
I
If I had
have
to guess.
no idea. Basically, it was a 2-year project, pretty non-stop. But the main bulk of that was designing or doing all the little circuit diagrams in Paint. I say little, they're like almost tens of thousands of pixels across. But the actual wiring for this particular model didn't take too long. I mean, each module took me, I remember, recently Facebook Memories sent me a link to one of the pictures of this saying, just spend 3 days wiring this up solid. So I'm guessing it took me about 3 days to do the main logic unit. God knows how long it took to actually debug that and get it working. Same with each unit. So basically it's very modular, so each unit was made separately. And it would, that's that side gone. And then each module was made, each module was debugged, and then they all had to kind of be wired together. Yeah, so, I mean, I can't actually hold this up, but if after the talk you guys want to come have a look, I can power it up and on the desk and show it working and talk through some of the bits. The great thing about relays, you can just plug LEDs on any of it and it lights up and looks really pretty. And also helps for debugging when you can remember what all the LEDs do, which 90% of the time I can't. But see if I can get it to run while open. No, not really. Can't pull the paper tape up. I'll have a fiddle, see if I can get it to work. But yeah, if anyone wants to come up and have a look, it's more than welcome to.
Yeah. Does anyone got any other questions? Oh, we've got one over here.
Slowly going.
Bit of a random question. Have you ever set Tim up on a table on a train just to see what people's reactions would be?
I did consider taking it into my GCSE final GCSE exam when I had Tim 6. Unfortunately, I think I was told I couldn't because the noise would be distracting. But the general idea was to get it to a point where I could run programs on it. It doesn't really transport very well, although it is 12 volts, and I have considered making it battery powered. But it's not really a PC. I've always wanted to try and get it to, I've always joked about the fact it could run Windows if it had enough memory and time, but now I've got a terminal. You could almost write an operating system for it, but I'm not quite sure how much you could actually do with it and how awfully slow it would be.
Be interesting if it did run Windows. How long would it take to boot?
Yeah. Unfortunately, there's not very much light in here, so I'll try and get some data in the relay.